Imagine a battlefield where a single machine can turn an area the size of a small city into a scorched desert in a matter of seconds. 12 shells shoot into the sky, one after another, and within a minute, nearly 68 hectares of land cease to exist as they were. This is not science fiction or an exaggeration. These are the real characteristics of the Russian Tornado-S multiple launch rocket system, a machine from which it is impossible to hide at a range of 200 kilometers. And to understand how Russia created a weapon of such power, we must go back several decades to the era when Soviet designers laid the foundation for the most destructive multiple-launch rocket systems on the planet. It all began with the Smerch, the legendary Mlrs, which entered service with the Soviet Army in 1987. For its time, this system was a true breakthrough. 300mm caliber, firing range up to 70 kilometers, 12 launchers. The Tornado terrified any enemy and had no equal in the world in terms of its combined characteristics. It was developed at the Tula State Scientific and Production Enterprise Splav, the same design bureau that had earlier given the Army the famous Hail and the no less formidable Hurricane. The Soviet school of multiple-launch rocket systems was already considered the most advanced in the world by that time, and the Tornado-S became its pinnacle. However, time passed, and by the early 2000s, it became obvious that even such a powerful system needed extensive modernization. The world had changed dramatically. High-precision weapons had emerged. Satellite navigation was no longer the prerogative of strategic missiles alone, and the battlefield was dominated by speed of decision-making and precision of strikes. The Smerch, for all its destructive power, struck an area, and its unguided missiles flew on a ballistic trajectory with no ability to correct. For the late 20th century, this was acceptable, but new realities demanded a fundamentally different approach. The designers at Tula understood this better than anyone. They were the ones who created the Smerch, and they were the ones who undertook its extensive modernization, which, in essence, was supposed to give birth to an entirely new weapon system. The goals were ambitious: to increase the firing range at least double, achieve a fundamentally new level of accuracy using guided projectiles, and automate all processes from aiming to firing. And most importantly, to ensure that each of the 12 projectiles could fly to its own target, not simply cover a square on the map, but strike specific targets with an accuracy that Smerch operators could only dream of. Work on the new system, designated 9K515 and named Tornado-S, spanned many years. It wasn't simply a matter of replacing one component with another. Designers had to rethink the very concept of a multiple-launch rocket system. Previously, Mlrs had been perceived as an area suppression tool, but now it had to become a high-precision weapon capable of striking specific targets at enormous distances. In fact, the line between classic rocket artillery and tactical missile systems began to blur, and the Tornado-S found itself at the forefront of this process. A key decision was the integration of GLONASS satellite navigation into the missile guidance system. By that time, Russia had already deployed a full constellation of 2 satellites in orbit, and the system's designers were able to use this system to correct the missiles. The idea was elegant in its simplicity. Add a relatively inexpensive GLONASS receiver and an associated autopilot to the existing missile design, allowing the projectile to adjust its trajectory throughout its flight. This provided a colossal increase in accuracy at a relatively low cost. In 2017, the Tornado-S officially entered service with the Russian Army. By this time, the system had completed a full cycle of tests and confirmed all its stated characteristics. The firing range increased to 120 kilometers, compared to 70 for the earlier Smerch. Accuracy increased significantly thanks to satellite correction, and the automated control system reduced the preparation time for firing to a minimum. The Russian army received a weapon whose capabilities were unparalleled by any other army in the world. Tornado S production was launched in Perm at the Matavalika plants, at the oldest defense enterprise in the Urals, whose history dates back to the 15th century. It was here, on the banks of the Kama River, that they began assembling the combat and transport loading vehicles of the new complex, and it was from here that they were dispatched to the troops. The choice of site was far from random. The Matavalikan factories had specialized in artillery systems for decades and possessed all the necessary production facilities for producing equipment of this class. But to understand just how significant a step forward the Tornado S has made compared to its predecessor, it's worth understanding how each vehicle in this complex is designed and what exactly has changed. The heart of the system is the 9A5415 combat vehicle. This is not, it's simply a launcher on wheels. It's a fully fledged, autonomous combat system, capable of independently determining its location, plotting a route, and aiming the launcher at its target without the crew ever leaving the cabin. It's based on an 8-wheeled, all-wheel drive tractor with 15-meter diameter wheels, capable of traversing off-road terrain, fording rivers, and climbing steep inclines. Weighing 43.7 tons, this vehicle accelerates to 85 kilometers per hour on the highway, which is excellent for a vehicle of this size. Under the hood is a 12-cylinder diesel engine producing 525 horsepower with a cruising range of 850 kilometers. This means that the combat vehicle can undertake long marches under its own power without being tied to railway platforms or heavy trailers, quickly change positions, and evade counterattacks. On the battlefield, mobility often means survival, and the designers understood this perfectly. But the main difference between the 9A54 and the Smerch combat vehicle lies not in the chassis, but in its electronics. The onboard equipment allows the vehicle to autonomously perform axleing and navigation, displaying the current position on an electronic map. The crew no longer needs to deploy surveying equipment and manually determine the coordinates of the firing position. The onboard computer does all this in a matter of seconds. Automatic guidance of the launcher package is performed using data received from the command vehicle. However, if necessary, the crew can switch to manual control. The operator fires using a special control panel directly from the cockpit, and no crew member is exposed to danger during a salvo. The second vehicle in the system is the 9T255 transporter loader. And here, a true revolution has occurred in the speed of preparation for a second salvo. With the old Tornado, the reloading process was a long and labor-intensive affair. The 9T2342 transporter loader vehicle loaded 9 M55 missiles into the combat vehicle's launch tubes one at a time using an onboard crane. And even for the most experienced and coordinated crew, this procedure took at least 15 minutes. A quarter of an hour in an open position when the enemy can already detect the launch point and make a retaliatory strike is critically long. The designers of the Tornado S have solved this problem radically. The missiles of the new system are placed in special transport launch containers, and the crane of the transport loading vehicle installs them whole, not individually. The result is impressive. A full reload of the 12 launchers takes no more than 3 minutes. From 15 minutes to 3, this is a 5-fold reduction in time, which in real combat can mean the difference between the life and death of the crew. The combat vehicle has time to fire, receive new ammunition, and leave its position before the enemy has time to react. The third element of the system is the 9S936 command vehicle. This is the brain of the entire system, from where fire control for the entire division is exercised. The command vehicle's onboard computer receives target data, automatically calculates firing parameters, and distributes tasks among the combat vehicles. The automated guidance and fire control system allows for the simultaneous coordination of several launchers, making the Tornado S division's salvo truly devastating. The entire crew of each vehicle consists of only 3 people.
3 soldiers operate the system, capable of destroying all life within an area of almost 70 hectares. Moreover, automation has reached such a level that the time from receiving target designation to the first shot is minimal. The system deploys from its travel position to its firing position, aims at the target, fires a salvo, and retracts with such speed that it is extremely difficult for the enemy to track and hit the firing position. If the combat vehicle is the body of the system and the command vehicle is its brain, then the Tornado-S shells are without exaggeration its fists, and incredibly precise and destructive fists at that. It is in the ammunition that the main technological breakthrough that separates the Tornado-S from its predecessor, the Smerch, is concentrated. It differs as decisively as a guided missile from a conventional artillery shell. The core of the arsenal consists of 2 types of guided rocket projectiles, the 9M540 and 9M549. Both have a caliber of 300 millimeters, a length of 7.6 meters, and a weight of approximately 830 kilograms. In terms of dimensions and weight, they're virtually identical to the previous generation of ammunition designed for the Tornado. This was a conscious decision by the designers. It will retain compatibility with existing launcher rails and transport containers. However, inside these missiles is a completely different internal component, which makes the Tornado-S a new generation weapon. The design of both missiles is based on a cylindrical body with an ogival nose cone, that is, a fairing of characteristic elongated shape and a tapering tail section. The nose cone is equipped with 4 folding aerodynamic fins, which deploy after the missile leaves the launch tube and provide flight control for the aircraft.
Its trajectory. These rudders, receiving commands from the autopilot, correct the missile's course with a precision unachievable by the Smerch unguided missiles. The tail stabilizer, whose design is truly original, deserves special attention. Its planes are attached to a ring-shaped base that rotates freely around the missile body. Thanks to this solution, the stabilizer spins in the oncoming airflow, ensuring flight stability. However, the missile body itself remains stationary and does not rotate around its axis. It would seem that this detail is purely engineering, but it is precisely this detail that made possible the full use of satellite navigation on board the missile. A rotating missile creates enormous difficulties for the operation of the navigation receivers in the autopilot, while the stationary body allows the electronics to operate stably and without interference throughout the entire flight. A unified control unit is located under the nose cone of each missile. This is the missile's most complex and expensive component. It includes an inertial navigation system, a GLONASS satellite navigation receiver, an autopilot, and electric control surface actuators. The strapped-down inertial system tracks the missile's position in space from the moment of launch, and the GLONASS receiver continuously updates its data using satellite signals. The 2 navigation circuits work in tandem, complementing each other, ensuring the exceptional accuracy that distinguishes the Tornado-S from all previous multiple-launch rocket systems. But the missile must not only reach its target accurately, it must also be guaranteed to hit it. And here, the 2 types of ammunition complement each other. The 9M54 projectile carries a cluster warhead containing 552 shaped charge fragmentation submunitions, each weighing 240 grams. Each submunition is capable of penetrating 140 millimeters of homogeneous armor and simultaneously disperses fragments over a radius of several meters. A single projectile, opening its cluster warhead over enemy positions, rains down more than 500,000 deadly submunitions, making it virtually impossible to hide from this rain. The second projectile, the 9M54-9, carries a different type of cluster warhead, 72 larger fragmentation submunitions. Each submunition has a significantly greater mass and lethal area. This makes this munition particularly effective against armored vehicles, artillery batteries, and stationary targets.
Thus, the battalion commander can select the type of projectile depending on the nature of the target. Small shaped charge fragmentation elements against infantry and light vehicles, or large fragmentation elements against heavy armored vehicles and fortifications. For both projectiles, the designers developed a new solid-fuel rocket motor with increased efficiency. This motor has allowed the maximum firing range to be increased to 120 kilometers, while earlier Smerch missiles could only fly 70 kilometers, in later versions 90 kilometers. An increase of 50 kilometers or more while maintaining the same dimensions in weight of the projectile is a significant engineering achievement, made possible by a new propellant composition and an optimized motor design. The minimum firing range is 15 kilometers, allowing the system to be used at relatively short distances if necessary. Another fundamentally important feature is the ability to assign each projectile an individual flight mission. This means that 12 missiles in a single salvo can fly not just to a single target square, but to 12 different targets, separated by a significant distance from one another. The guidance unit of each projectile receives its own target coordinates before launch, and after leaving the guide, the missile follows an individual trajectory. Essentially, a single Tornado-S salvo is equivalent to 12 separate high-precision strikes delivered practically simultaneously. Any precision weapon is only as effective as the precise target coordinates programmed into it. You can create a perfect missile with a flawless guidance system, but if it flies in the wrong direction, the entire technological breakthrough will be meaningless. The Tornado-S designers understood this from the very beginning, and therefore the issue of target reconnaissance and precise coordinate determination became one of the key priorities in the system's development. The foundation of the Tornado-S's precision is the Russian GLONASS Global Navigation Satellite System. Its 24 satellites are deployed in circular orbits at an altitude of 19,400 kilometers above the Earth's surface. When working together with a pair of Luch series relay satellites, the constellation ensures coordinate determination with an accuracy up to 1 meter. It is a proprietary navigation system, completely independent of foreign countries, and it is precisely this system that allowed Russian designers to transform the multiple launch rocket system from an area effect weapon into a high-precision instrument. According to some sources, the circular error probable for salvo firing is 0.3% of the firing range. If we translate these figures into specific figures, then when firing at a maximum range of 120 kilometers, the projectile's deviation from the aiming point does not exceed a few hundred meters, and according to some reports, the designers achieved an accuracy of a few meters. The exact figures are classified for obvious reasons. However, the very fact that we are talking about meter-level accuracy for a 300mm caliber rocket speaks to a colossal technological leap. However, satellite navigation only solves half the problem. It ensures precise guidance of the missile to specified coordinates. But before guiding the projectile, these coordinates must be obtained. The target must be detected, recognized, and precisely referenced to the coordinate system. In modern combat, when the enemy actively camouflages itself and constantly changes positions, this is an exceptionally complex task. This problem must be solved by space or aerial reconnaissance using optical, infrared, and radioelectronic surveillance equipment. And here, Russian designers have adopted a solution that can be called truly elegant. An experimental 9M534 projectile was developed specifically for the Tornado-S system. This munition does not carry explosives, but a compact T-90 reconnaissance unmanned aerial vehicle, which is part of the Tipchak system. The idea is that the multiple launch rocket system provides itself with reconnaissance data by firing the reconnaissance drone at the suspected target area. The operating principle of this projectile deserves a detailed description. After launch, the missile flies to a pre-reconnoitered area where the enemy's targets are presumed to be located. Over this area, the cluster munition warhead deploys, and the T-90 drone emerges. The device begins to descend by parachute and simultaneously activates its onboard surveillance equipment, scanning the situation below. For 20 minutes, the drone transmits real-time video information to the RCDC command post, as well as to the command posts of other artillery or tactical missile systems operating in the area. 20 minutes of aerial reconnaissance is a massive amount of information. During this time, operators at the command post can detect and identify targets, determine their precise coordinates, and decide whether to destroy them. The coordinates are immediately transmitted to the combat vehicles, which by this time are already in firing positions and ready to fire. The vehicles were geolocated using GLONASS signals and determine the azimuth and elevation angle to deploy the launch guides. Next, the combat control and communications equipment, which on the Tornado S replaced the standard radio station of the old Smerch, comes into play. This equipment operates in conjunction with the automated guidance and fire control system on a single digital platform, thereby achieving full integration of communication functions and the ballistic computer. The command vehicle transmits target data. The combat vehicle's onboard computer calculates the firing parameters, and the launch guides deploy to the desired position. At the moment of launch, the missile leaves the transport and launch container. From this second, the onboard missile guidance system begins autonomous operation. The stabilization system continuously receives data from inertial sensors and adjusts the rocket's motion using gas dynamic rudders, compensating for engine thrust asymmetry, cross-wind gusts, and other disturbing factors. Simultaneously, the GLONASS receiver captures satellite signals and begins to determine the rocket's current coordinates in space. Two navigation loops, inertial and satellite, operate in parallel, constantly comparing data with each other. The inertial system provides instantaneous information on the missile's position, but accumulates error over time. GLONASS provides absolutely precise coordinates, but with a slight delay. Together, they form a closed correction loop, where satellite data continuously refines the readings of the inertial sensors, which in turn fill in the gaps between satellite signal updates. The projectile flies toward its target, constantly adjusting its trajectory, and at the final point, the deviation from the specified coordinates is minimal. One of the most far-sighted decisions of the Alloy's designers was to maintain the Tornado S's full compatibility with older missile types developed for the original Tornado. At first glance, this may seem like a minor detail, but in real-world, intensive combat conditions, this feature takes on enormous significance. High-precision guided missiles with satellite navigation units are technically complex and expensive to produce, and in war, ammunition is expended at an incredible rate. And when the supply of guided missiles runs out, the Tornado S crew is not left unarmed. They can load unguided projectiles from the Tornado S and continue to carry out combat missions. This gives battlefield commanders incredible tactical flexibility. Receiving a mission to destroy a specific target, a command post, an anti-aircraft complex, or a communication center, the division uses 9M54 or 9M549 precision-guided projectiles, each of which flies precisely to a designated point. And if the task is to cover an area target, a concentration of vehicles on the march, a field camp, or a personnel concentration area, one can use older, unguided rockets, of which there are significantly more available in warehouses and which are significantly less expensive. Essentially, the same system combines the capabilities of precision weapons and classic rocket artillery, and switching between these modes is accomplished by simply replacing the ammunition. In 2021, the development of fundamentally new 300mm rockets for the Tornado S became known, and the characteristics of these munitions have forced military experts around the world to reconsider their ideas about the capabilities of multiple launch rocket systems. The new missiles have a range of 200 kilometers, almost 3 times greater than the previous Smerch missiles, and significantly greater than the 120 kilometers of the basic Tornado S projectiles. At the same time, the designers retained all the control and navigation systems, ensuring the highest target accuracy at this incredible distance. 200 kilometers is a distance at which the enemy can feel deep in the rear, far from the line of contact. Headquarters, logistics centers, airfields, ammunition depots are all within the range of the multiple launch rocket system, which until recently was considered a purely tactical close combat weapon. The Tornado S, with its new projectiles, has effectively crossed the line between the tactical and operational tactical levels, becoming a tool capable of influencing the course of events far beyond the front lines. As early as 2022, reports were received that the Tornado S system had been equipped with these high-precision projectiles with extended range. The system, which was already one of the most powerful MLRSs on the planet, received another serious argument. Moreover, the new ammunition did not require any changes to the design of the combat vehicle itself. They are fully compatible with existing launch rails and transport and launch containers, which significantly simplifies their introduction into the military. The modern battlefield is unthinkable without unmanned aircraft, and the Tornado S fits perfectly into this reality. In addition to the already described reconnaissance projectile with a drone, the system is increasingly operating in conjunction with various reconnaissance drones, which provide target designation in real time. The drone detects a target, determines its coordinates using its own navigation systems, and transmits the data to the division's command post. From there, the information is immediately transmitted to combat vehicles, and within minutes, a high-precision strike is launched against the target. The detection-to-destruction cycle is compressed so much that the enemy simply doesn't have time to leave their position. According to available data, the Russian army has approximately 20 Tornado S units in service, and production at the Motovelikinsky plants in Perm continues. Each new vehicle leaving the factory floors increases the firepower of missile artillery brigades and gives commands another tool for solving the most complex combat missions. And given the constant improvement of munitions, from basic guided missiles to the latest projectiles with a range of 200 kilometers, the potential of this system is far from exhausted and will only grow. If you are interested in learning about the capabilities of the Tornado S and why this system is rightly called one of the most fearsome weapons on the planet, please like this video. This way you'll help promote our content and let us know that you're interested in such topics. Be sure to subscribe to the channel so you don't miss new episodes, and let us know in the comments which weapons you'd like to hear about next.